Okay, good day, sir. My name is ROOBAKKANTHAN Jayabalan. My metric number is B0821103889. So today, I and NAZRUL like to present about Lab 3, the infinite impulse response filter design. So I take the part 1 topic. Before that, I will explain about the introduction. So for the infinite response filter, are a type of digital filter that has been feedback component, unlike FIR filter that only use feed forward coefficients. This feedback loop in IRR filter is responsible for the infinite response, which means the impulse response does not decay to zero after a certain time, or as opposite FIR filters. So the given MATLAB code demonstrates the design of an IRR low pass filter based on the IRR Butterworth filter designing utilizing the bilinear transformation method. This process involves determine the filter parameters such as the filter order and the calculating the feed forward and feedback filter coefficients. For the first part, the pass band and stop band parameter. For the pass band and the stop parameter frequency are specified in normalized form as PS nor and SP nor respectively. These normalized frequency are then converted to a radians by multiplying them with pi PS nor and pi SP nor respectively. Maximum pass band ripple in the decibel is given by PS max def dB, which is this one, and converted to a linear scale as PS max div. For the maximum stop band magnitude decibel is given by SP magnitude mac dB, which is negative 15, and for the SP mac equals to 10 power of SP mac dB divided by 20. For the filter parameters, E is calculated as square root of 1 over SP max def power of 2 and minus 1. For A is set up to a 1 over SP max mac. For K1, E over square root of A power of 2 minus 1. The filter parameters are calculated based on the pass band and stop band specification given as input for designing an IIR low pass filter using the Butterworth design and the bilinear transformation method. I will briefly explain about the key calculation involving the MATLAB code. Calculating the E and A and K1. E is the square root of the quotient of 1 over PS max def power of 2 and minus 1, representing the normalized frequency for the pass band based on the maximum pass band deviation. A is calculated using the maximum stop band deviation XP max is sets the magnitude of the frequency response for the stop band. K1 is derived using E and A as the ratio of E divided by the square root of A power of 2 minus 1. Calculating the frequency mapping PS alpha angle, the frequency mapping is calculated using the tan function for the pass band and stop band angles. This enables the mapping angular frequency from Z domain or digital domain to the S domain, which is continuous domain, using a scalar factor T equals to 2. And calculating the transition of ratio K derived as the ratio of PS alpha angle and the SP alpha angle. This ratio represents the amount of attenuation required the transition from the pass band to the stop band, computing the Butterworth filter order. So, example, I will run the program. Okay. For the calculation, here is the PS angle 0.628 PS max respectively for the each one, SP max and E, AK1, PS alpha N and SP alpha N, and also for not. Not is equal to 4. So as for the examples, I've done two examples that I changed the PS nor to 0.4 and I changed the maximum deviant dB into the -5 and SP no I changed to 0.2 for the SP max magnitude of dB I changed to -10. Okay, as for the result we run. Okay, here the result is max deviant is 0.5 and PS max magnitude is 0.3162. Okay, as for the K, we got 2.2361 and as for the north, 0. For the second example, I've changed my PS north to 0.5 and SP north to 0.8. For the PS max dB, -6 and SP max dB to -30. So we run these. I got not is equal to 3 and K equals to 0.3249 and the K1 is 0.0546 and A is 31.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iskandar. I will continue our presentation by showing part 2, low pass IIR filter design. So in the MATLAB, my friend already present about part 1. So for the part 2, low pass IIR filter design, we create the pass band, which is the pass now is 0.2. And the stop band is for part 2 Espino is equal to 0.3. For part 2 we try to find the cut alpha angle, the polynomial and n polynomial. So basically cut alpha angle is represent third decibel, cut off angular frequency of the design filter. A is also the angular frequency at which the magnitude response of the filter is -3 decibel. For D-poly is actually a denominator polynomial of the filter transfer function in the Laplace domain is analog filter. And the last one is N-poly. So N-poly is a numerator polynomial of the filter transfer function in the Laplace domain analog filter. So it represents the coefficient of the numerator polynomial of the filter transfer function. So this is the result after we run part 2, that 3. So here we know that the passband here is maximum is 0.2 because we set in the codes passband is equal to 0.2. And meanwhile for the stop band will start here from 0.25 until 3.2. So this is the result of part 2 for the graph. Here is we get a cut alpha angle 0.3251. The polynomial is 89.5086 and n polynomial is 1. So that's all for part 2 in our lecture. So here for example we change the PS no to 0.1 and also the stop band also remain changed, which is 0.25, and that's all I will change. So the result also the same. We want to find the cut alpha angle and the polynomial and also also an polynomial. So we run it first. So as you can see here, the result are totally different. So because we set the stop band and the pass band different from the part 2. So in this part 2 example, I put the pass band which is equal to 0.1. So here is the pass band 0.1. Then for stop band 0.25. So this is stop band 0.25. 0.25. Okay. So this is the comparison of two of the part 2 and part 2 of example. So as you can see here, the difference of part 2 and part 2 example is only the pass band, because we only changed the pass band for part 2. The pass band is 0.2, meanwhile the pass band for uh, part 2 example is 0.1. So that's why the pass band is look thin. It looks thinner than the part 2 example. So next we go to application of low pass IR filter. So there are many applications in this world that are using this filter. So for example, biomedical signal processing, which is actually mass produced and widely used in medical signal, such as electrocardiogram, ECG, and encephalogram. So for noise removal, artifact suppression, and features extraction, enabling accurate diagnosis analysis. So number two example is control system. So IR filter are applied in control system to shape the frequency response of feedback loops, stabilize and improve any transient response for achieving desired system performance. The last thing is speech and audio compression. So basically, speech and audio compression are employed in speech and audio compression algorithms such as speech codecs and audio codecs to achieve efficient data compression while maintaining acceptable audio quality. Uh, so in speech and audio compression is actually this filter will remove any uh, what we call bad noise. So this filter is important in speech and audio compression. Thank you very much.
From here, I can conclude one thing about this one, which is the infinite repulse response I filter, as demonstration in the MATLAB code, is a design for low pass filter based on the IIR Butterworth filter approach, employing the bilinear transformation method. The code calculates the crucial parameters such as filter order, frequency mapping, transition ratio, and the essential filter parameters based on the pass band and stop band specification. The resulting filter design meets the necessary design criteria, enabling a digital filter implementation that efficient in terms of computational complexity and resources utilization when compared to FIR filter. The design is applicable for signal processing and control application where a customized low pass filter makes a difference in improving signal quality and system performance. So that's all from us. Thank you.